Welcome to AWS IAM Authentication in MongoDB Atlas clusters, or secure passwordless authentication. Today I am introducing a new way to authenticate with MongoDB Atlas using the familiar AWS IAM service. Hi, my name is Mark Benvenuto. I have been with MongoDB for 6 years and was a technical lead on this project. I also led the technical design for the field-level encryption project in MongoDB 4.2. Today we will cover 4 main topics. First, I will discuss the current state of authentication for Atlas clusters. Next, I will present the new authentication mechanism we added. I will then explain how it can be used to make Atlas more secure and how it works. Finally, I will discuss availability. The focus of this talk is going to be about authentication to MongoDB Atlas clusters. We will not be talking about the Atlas website and the various mechanisms available for it. Instead, the focus will be on how the drivers and shell can talk to Atlas clusters. Today, we support 3 types of authentication in MongoDB Atlas clusters. MongoDB's authentication systems is built around an open standard for authentication called Simple Authentication and Security Layer, or SASL for short. This is an open standard published by the IETF, the Internet Engineering Task Force. In Atlas, we support 2 SASL mechanisms: SCRAM, i.e. Salted Challenge Response Authentication Mechanism with a SHA-1 hash algorithm, and plain. SCRAM allows you to prove a user knows a password to MongoDB through the magic of HMAC without sending a password over the wire. Next, we support LDAP via the SASL plain mechanism. This allows customers to use their existing LDAP solution for authenticating users with MongoDB. Finally, we support X509 certificate authentication, which is not a SASL mechanism, but simply builds on the TLS protocol's existing support for client authentication. By the way, on-premise MongoDB has the same set of authentication mechanisms, plus it offers a passwordless mechanism in the form of Kerberos, otherwise sometimes called GSAPI. Here is a picture of a canonical application in AWS that uses a mix of storage services for storing data. In the center, the app consists of a stateless application runtime on a set of containers in the AWS Elastic Container Service. On the left, AWS Elastic Load Balancer is used to route requests to the containers. On the right, the app stores application data in a mix of AWS Simple Storage Service and MongoDB Atlas. The app uses S3 to store large files like photos because S3 is efficient at storing large binary files. On the other hand, it uses MongoDB Atlas to store metadata about those photos for its document model and rich query support. Now, if you look closely, we have 2 different authentication paths in this diagram highlighted in different colors. The orange color highlights the AWS IAM Auth, which is built into AWS. It allows containers to talk to the load balancer and S3. The green color highlights the MongoDB Atlas code path. It is used by the container to talk to the MongoDB Atlas cluster. It supports a rich variety of authentication mechanisms as outlined before. Unfortunately, while this application architecture is powerful, it comes at a cost of complexity and other issues because of the 2 sets of authentication mechanisms in use. MongoDB's goal is to make it super easy for developers to build modern web applications. With that in mind, there are 2 sets of issues that arise with the previous diagram. The application to Atlas cluster experience, simply, we have 2 different sets of credentials and authentication mechanisms to manage. For the DBAs trying to administer the Atlas cluster, they have one way to authenticate with AWS services and yet a different way to authenticate to Atlas clusters. For the application to Atlas cluster, 2 different authentication mechanisms equals 2 different sets of secrets to manage. The authentication among all the AWS services is AWS IAM Authentication. This is a seamless cross-service experience that does not require managing passwords, whereas the MongoDB SCRAM or LDAP mechanisms require applications to provide a password. Now, for MongoDB Atlas, where do you store the password? Do you store them encrypted as a variable in the container task definition? Do you instead store them in AWS Systems Manager Parameter Store or AWS's secrets manager? Or how about a third-party system like HashiCorp's Vault? Depending on your solution, you may incur costs to retrieve your secure secret as the AWS services charge by request, additional charges for storing the secrets, and we've not even discussed how to rotate them yet. This is an operational burden to take on just to use two systems in your application. For the DBA, there are different ways to connect to the different AWS versus MongoDB Atlas cluster. This means there are twice the number of credentials that need to be managed, stored, and periodically rotated. And while MongoDB Atlas and AWS both support generating temporary credentials, they are incompatible with each other. This means that DBAs or DevOps now need to talk to two separate systems if they need temporary credentials to talk to sensitive applications. And while the Atlas UI supports multi-factor authentication, MongoDB Atlas clusters only support it when using LDAP. But what if there was another way? Now imagine a world where there's only one way to authenticate to your AWS services and MongoDB Atlas clusters. In this world, the application can use a single set of AWS credentials to access AWS services and MongoDB Atlas clusters. You'll notice the arrow connecting to MongoDB has been changed to be orange to match the rest of the arrows. The same set of credentials that the container uses to access S3 can be used to access MongoDB Atlas clusters now. No longer is there a need to manage a separate set of credentials to access the MongoDB Atlas clusters. Oh, and if you need cross-cloud, that also works just fine with the new authentication. This diagram highlights using a mix of Google Cloud Engine, AWS, and MongoDB Atlas in the application. But just note that everything works just as well if we had Microsoft Azure in the picture. MongoDB is committed to cross-cloud, and this is just one more example. It does not matter where the Atlas cluster is hosted or where the application is hosted. Everything just works. Introducing a new authentication mechanism for MongoDB Atlas clusters named MongoDB-AWS. A unique new way to work with your MongoDB Atlas clusters that offers seamless integration with AWS. The new MongoDB-AWS authentication mechanism is available with MongoDB 4.4 Atlas clusters at the M10 level and above. It is exclusive to MongoDB 4.4 clusters and MongoDB Atlas. It supports cross-cloud. It does not matter which cloud providers your application or your Atlas cluster are hosted in. You can freely mix and match cloud providers. The new mechanism is supported by all official MongoDB drivers and the shell. Furthermore, it has deep integration with various AWS services, which I will go into. The new authentication mechanism builds on the existing AWS IAM and security token services. We support the STS Assume Role API. We also integrate with AWS's multi-factor support because of our support for Assume Role. The new authentication mechanism has been tested and integrates with Lambda, EC2, and ECS. Finally, we support authentication for both IAM users and roles. As mentioned on the previous slide, MongoDB-AWS supports two different types of AWS IAM types. The first, IAM roles, are typically used for applications for service-to-service authentication, but can also be used in functionality like Assume Role. We will revisit our Canonical application and show how it works with the IAM role in a few minutes. This is a very powerful feature of AWS IAM. It works very well when paired with the MongoDB Atlas clusters. The second IAM type that is supported is IAM users. These are typically used by human operators. You typically use them with a program like the shell. Now, moving on, let's talk about role authentication. Role authentication is the most powerful feature and where the new authentication mechanism shines. There are two users of role authentication, applications and users who assume a role. In the first case, your application will be running on an EC2 machine, an ECS container, or in Lambda. I will go into this more in the presentation. In the second case, you can use STS Assume Role functionality to assign permissions to roles and then control which users can assume that role. For instance, you might have MongoDB app role operator that grants all the actions needed to manage all the pieces of the example AWS Canonical application. Then instead of granting users that role, you grant them the ability to assume that role, which can be better audited and managed. This added layer of indirection makes permissions easier to manage since you can organize roles around tasks, and it also supports multi-factor authentication. Here's a screenshot of what it looks like in the Atlas UI to actually add a role. First, select AWS IAM as the authentication method. Next, select IAM role for the AWS IAM type. Finally, enter your AWS ARN. Notice there is no password stored. I'll explain more about that later. As we saw in the previous screenshot, adding an Atlas user that authenticates via an AWS IAM role is very easy. To start, you just need the ARN for the role and then choose to add an AWS role user. On the AWS side, you just need to assign the same role as the execution role to your container, EC2, or Lambda function that hosts your application. You do not need to grant any special AWS actions to the role to make it work with MongoDB. For your application, it is even simpler to add support for MongoDB-AWS. You just update to the new URL that points to your cluster, and you're done. You do not need to specify a username or password anymore. Note, the URL does not contain a password. If you notice in the previous slide, there was no password, but we were still able to authenticate to our MongoDB Atlas cluster. So you may be asking, what's the catch? Is it really passwordless? Yes, but while there is still a password, you no longer need to manage the passwords. That is the important part. AWS services support execution roles. Execution roles allow you to assign an IAM role to either an AWS EC2 machine, ECS container, or Lambda function. You can then associate permissions to this role and allow it to access IAM services. Under the covers, AWS provides the application running on one of these compute services with a set of temporary credentials that can be used by the application to talk to AWS services. When you use an official AWS SDK, the SDKs automatically retrieve these credentials for you. We've mirrored the same functionality as the AWS SDK into the official drivers for MongoDB 4.4. When you pass it a connection string for MongoDB-AWS, the driver will seamlessly use the temporary credentials for you. We've also designed it for the most sensitive security situations. Your secret key is never passed to MongoDB Atlas clusters, is never persisted by the driver. I'm going to go into more detail and explain how that works over the next few slides. These slides will make it clear why the password is never sent over the wire to the Atlas clusters. When you log in with the new authentication mechanism, MongoDB-AWS, there are three pieces involved in the login handshake. The first piece of the puzzle is your application with a driver that supports a MongoDB 4.4 Atlas cluster. All the official drivers have support for the new authentication mechanism. The second piece is a MongoDB Atlas cluster running MongoDB 4.4. The new auth method is only supported in M10 clusters or above. And finally, the AWS security token service, which the MongoDB Atlas cluster uses to validate the credentials. This is a standard service available in all AWS regions. There's nothing to enable or configure on a user's end. We are going to revisit our Canonical application from earlier and explain how it all works with the new authentication mechanism. First, on the far right side of the slide, you will notice that we've added the AWS security token service, the red box, which is used by the Atlas cluster. The MongoDB Atlas cluster talks to the STS service to validate the identity of the user. The next set of slides will break down the one-time setup in AWS and Atlas, and then I will break down the three main steps in authentication. The first step in the one-time setups is set up the AWS service with support for temporary credentials. First, you create an IAM role. You don't need to assign any special AWS actions for MongoDB Atlas. The authorization checks are still done by MongoDB Atlas in this case, not AWS. That's why there's no need to add any particular actions to the IAM role. Next, you need to assign the IAM role to an ECS container. To do this, you assign it a task execution role in the ECS task definition. The act of assigning a IAM role to an ECS task enables the MongoDB driver to get temporary credentials at runtime. Please note that if you have an existing task definition, you may not need to make any changes. If the container already accesses an AWS service like S3, or needs to retrieve images from a private Elastic container service, it will already have a task execution role assigned to it. You'll just need to note the assigned role so it can be added in Atlas. In setup step 2, you need to add the task execution role as a user in the MongoDB Atlas cluster. Note that in this step, you do not provide any credentials to MongoDB Atlas. You only provide the ARN that should be permitted to log on to Atlas, just the string. Also, at this time, you must decide what set of permissions this ARN should have in Atlas. And that is all you need to do for the one-time setup. Setup complete. Now we discuss the 3 steps in the authentication process. The first step is to get the temporary credentials. These credentials have an expiration time and are periodically refreshed automatically by AWS. The MongoDB driver seamlessly retrieves them from the local machine, container, or Lambda function as appropriate. On the EC2 and ECS, the driver uses the AWS Instance Metadata Service version 2 to retrieve the credentials. IAM-DS v2 protects against server-side request forgery and was just released in November. This upgraded version of IAM-DS was released during the development of the Auth mechanism. We quickly pivoted our design to take advantage of it since it offered the most robust security. When run in Lambda, the credentials are exposed as environment variables to the function, so retrieving them is a lot simpler than making the HTTP calls required for the AWS Instance Metadata Service. Here is an example of some temporary credentials retrieved from IAM-DS v2. It consists of 3 important pieces that are highlighted in yellow and red. Going from top to bottom, they are access key ID, which is in yellow, secret access key, which is in red, and token, which is in yellow. These 3 pieces together allow the application to log in to a MongoDB Atlas cluster. But as I mentioned before, the secret access key, the red text here, is never sent to Atlas. I'll explain how it works in a moment. The access key and security token, the yellow text, are sent to Atlas. These are merely identifiers, not secret information, and are safe to transmit over a TLS connection to Atlas. In the second auth step, the driver sends the credentials to your MongoDB Atlas cluster. I will show you what is actually sent in the next slide, but let me emphasize again that the secret key is not sent. The driver specifically sends 3 pieces of information. These 3 pieces are a signature, which I'll explain later, the date and time the message was generated, and the security token. These 3 pieces allow Atlas and AWS to determine that the driver knows the secret access key without having to actually send the secret access key over the wire. This is an example of what the driver sends. If you notice, there are 2 yellow pieces of text. These pieces are the same pieces highlighted in the previous slide, the account key and the security token. As I explained before, there is no security key sent, which was highlighted in red text before. The most important piece of this content is the signature, highlighted in blue. A correct signature for a given access key can only be generated by something that knows the secret key. I'll explain more in a later slide how it is calculated. In the final step of authentication, the MongoDB Atlas cluster takes the signature and sends it on to the AWS Security Token Service. In this case, the Atlas cluster just makes a regular HTTPS call to the AWS STS service. The AWS STS service validates whether the signature is correct and replies with the ARN of the application that created the signature. After MongoDB gets an acknowledgement from STS, authorization information is retrieved from MongoDB. This means that all the role information, authentication restrictions, etc. for the IAM role are stored in MongoDB, not AWS in this case. Information about database role membership continues to be managed on the MongoDB side. Only authentication is managed by AWS. You continue to use Atlas for all your database role management. If the signature is incorrect or the temporary credentials are expired, for example, STS will return an error and the MongoDB logon fails. More information about why it failed can be found in the MongoDB error log. For MongoDB Atlas to verify the credential, it makes an HTTPS call to the STS GetCallerldentity API. GetCallerldentity is a free API that tells the caller the ARN of the account that generated the signature. You could call it yourself via the AWS command line or any AWS SDK. This could be used to identify which account an account key and secret key belong to, for instance. Finally, you'll notice that there are two yellow pieces of text highlighted above. These are the same yellow pieces of text highlighted in the first message example, the account key and the security token. As explained, there's no secret key, which was highlighted in red text before. The signature, highlighted in blue, is a compound SHA-256 HMAC calculation of all the headers in the body of the HTTPS request. The algorithm to compute the signature is rather involved and is called the AWS Signature version 4. It's documented in the AWS documentation if you want to learn more. To create the signature, you need to know the secret key for the account key. In our example diagram for our Canonical application, only two components know the secret key: the ECS container and the STS service. The driver gets the secret key from the temporary credentials and then tries to prove it knows the secret key by sending the signature to the STS service. The reason why the account key is sent to the STS service is so the STS service knows which secret key to use for computing the signature. The STS service verifies the signature is correct by recalculating the signature using its copy of the secret key. If it computes the same answer, then the request is considered valid and proceeds. If the signature does not match, a HTTP status code of 403, i.e. forbidden, is returned instead. Here's what a valid response looks like. The error of the role, highlighted in blue, is returned. This is checked against the list of users in your MongoDB Atlas cluster. If there's a user with the same name as this ARN, the authentication is successful. If no user was found with that ARN, the logon fails. As mentioned earlier, we also support user authentication. The process of adding a user is identical to adding a role. First, you select AWS IAM as authentication method. Second, you select IAM user for AWS IAM type. Third, you enter the AWS user ARN. Every user has an AWS ARN associated with them. There's a globally unique string that identifies an AWS account and user within that account. The ARN for a given user can be retrieved from the AWS console on the web page. Finally, to log in with this ARN, use the AWS access key and AWS secret key associated with that user. You do not actually log in with the ARN itself. That's why the ARN does not show up in the connection string. STS tells your MongoDB cluster your ARN if you know the correct secret key for the account key you specify. But please note, as we explained in the role authentication part of this presentation, the secret key is never sent to Atlas. Let me reiterate this point. Your secret key is never sent to Atlas. Atlas never receives your secret key. This is all possible by the cryptographic HMAC for the signature, which allows an application to prove it knows the secret key without sending it. With our discussion of how it works behind the scenes over, let's move on to how to use it in your application. We embarked on this feature to make it super easy for MongoDB users, and I'm proud to say it could not be easier to update your application to work with this new authentication mechanism. In short, all you need to do to make use of it is to update the URL your application uses. If you run it on EC2, ECS, or Lambda with an execution role, it simply just works. You can use the same code in all the different AWS hosted compute environments. For instance, if you started running your application first on EC2 and then decide to run on ECS, you do not need to make any changes to the code. As a bonus, after you update to MongoDB-AWS, you will likely be able to delete code as you'll no longer need all the previous code you had to read credentials. This slide is an example for the Node.JS driver, but it is just as easy to make the changes for any other language and driver. To recap, MongoDB-AWS is a new mechanism to authenticate with Atlas clusters. You can use AWS credentials natively across all AWS services and MongoDB Atlas clusters within your application. It works across Atlas clusters in Azure and GCP. It is available in MongoDB Atlas June 2020, and is supported in all official MongoDB 4.4 drivers. C, C++, C#, Go, Java, Node.js, PHP, Python, and Ruby. Thank you.